Good morning everyone. It is actually fantastic to see so many people here, particularly people I don't recognise in some cases, but also some I do. I have to thank a few people with my presentation because many of the people around and presenting today, I've managed to take bits out of their hard work to put on slides. But what I really wanted to do was to look at it more from a track engineer's point of view, some of the problems, but also looking at what's caused and what's actually happened on our infrastructure, give a bit of a flavour of it. Importance, we've seen some work already, some of the bits that have been done there. I spent a little time, what is it? And I've read a few books, looked at a few papers, done some research, various things. It's not that well defined. I think as a track system we can put it together, we understand that, but perhaps not so clearly defined. So what I've taken, it's a fairly simple thing, and from what I look at from the point of view, it's where the rails are under traffic, so how much they deflect elastically under an applied wheel load. You look at that, I'll show a bit more about why that's important, what makes that up. It's quite a complex thing. It's a function of many different parts and components. You've got rail pads, sleepers, under sleeper pads potentially, ballast, sub-ballast, formation, soil types, the geology. All of those make quite a difference, all add up to the overall system stiffness. That's what we're trying to achieve, is perhaps an optimum stiffness. A lot of debate about what that should be. I'm not sure there is a distinct answer, but depends on your traffic types. If you look at it, we've heard a bit already about it this morning. You look at ballast construction, some bits and pieces in there. You've got the rail, you've got the sleepers, you've got the pads, all very highly specified. I know exactly what stiffness that rail is, what the materials are, what the microstructure is. We've got ballast, specifications for the ballast. We've got specifications for the ballast depth in our construction standards. We've got specifications for crossfall, drainage, separator layers, sand blankets, lots of other bits and pieces there. And it stops. Nothing under there at all. So formation, very little there in standards about it. Starting to get good. Jeff's going to talk a bit more about some work to do with modelling, what we best understand. But even then, a lot of the models are fairly basic at the moment, but things are improving. We're starting to understand the importance. And if you look at some of the stiffness values, it's not a linear elastic spring, the formation. Often it's something there non-linear. It's not always elastic. Some of the problems there with settlement and permanent deflection. If you look at some of the components, soft track bed, perhaps about 10 meganewtons per metre per sleeper end. Typical track beds around 40, this is formation. Stiff track bed maybe as much as 100, so 10 times higher in that situation. The other bit we can really vary in there, around the pads, we can use soft rail pads, typical rail pads, perhaps a very stiff rail pad, but even there, it's a limited amount you can alter the overall formation stiffness. I've looked at some history, some measurements. We've got values, certainly we've actually measured physically in the UK for formation anywhere between 10 and 200 meganewtons per metre per sleeper end. You can see a big range there. And at the end of the day, probably formation stiffness is the most variable, probably the least well understood, and as Peter shows there, not the easiest to change. If we're going to try and change formation, it's a lot of work, particularly either in during construction, but also as a maintenance activity afterwards. So a very important part of the system, but perhaps less well understood and controlled. If you look at the variability, why? We've got various thicknesses, formations, soil types, geology, climate, moisture, drainage, compaction, settlement, it goes on and on, structures, transitions in particular. Something I've looked at more recently, I'll show a few results of some of that now. Quick plot there, the darker blue is areas of geology which is more inclined to high levels of shrink or swell. So moisture content there, the clay type areas, see quite a big movement in the track just because of the water content in there, so quite complex. If you look at the typical sort of bit of land, we put a railway on, Brighton Main Line in that situation. We've got about 6 or 7 different geological formations there on that. we've stuck a railway over the top. And ideally, we want to keep it nice and flat and level throughout the various conditions, changing climate. You can see there anything from London clay to Hastings sand as you go through there. So it's a linear asset, but may not be on anything like consistent formation. Some of the other things we worry about, we touched on a bit, from a track engineer's point of view, it's the localised or variable settlement really causes the problems. If it all moves together, perhaps not so much of an issue, but you can see there, these are just the line traces. Phil has touched on some of those with the rolling standard deviations, but you can see the rate of deterioration, where the track quality is very good, deterioration tends to be lower. Track quality is worse. This is an example where it has actually a problem with low formation. As it starts to deteriorate, the energy starts to increase, the deterioration rates start to increase. We end up with some quite significant problems then with geometry, trying to remove that roughness, which builds up over time, and a lot of the activities that track carry out are all trying to cure or correct some of those failures. If you look at the vertical loading, I'll come back to where sort of my heart lies to some extent. I've spent too long in rail management to give it up completely. If you look at some of the things we get, sharp changes in stiffness, wet beds, perhaps transitions to structures, measured quite a bit with factors there, dynamic factors up to 3 times more than you get on normal track. In some cases it can be even more extreme to that, but what you're looking at there is a significant change in what the rail is subjected to. It's also speed dependent, stiffness variations, so something that's very abrupt change in stiffness in high speed track is very damaging. Perhaps something that's a longer, softer or less significant change at lower speed, less of an effect. And a lot of these things don't necessarily manifest themselves on track traces and similar. You don't always see some of the effects that cause the damage to it. Ideally, the track wants to be flat, straight, supported on a perfect uniform stiffness. It's not all quite like that, but we do strive for it. Many of the other problems we see, it's not something that breaks the rail there and then. A lot of it's higher forces there. Most rail failures we see now are around fatigue type driven mechanisms. We may grow small cracks, initiate defects that then grow under normal traffic. So it's not always a sudden catastrophic failure, but some of the problems you see during the time, it may cause problems then at existing stress raisers. It's not absolutely continuous rail. We've got joints, fish plates, welds, other things, and then potentially inherent defects from manufacture within rail, but also as rail gets older, the effects of atmosphere, corrosion and similar on the outside. The big one, the rail life's generally dependent on the load it's subjected to and how long it's subjected to these loads. Fairly simple, but it comes back to fixing some of these faults quickly, getting there at lower intervention levels. Don't get it to a safety limit, perhaps even a maintenance limit. That increases the time it's under higher dynamic forces, and certainly most of the problems with some of the rail and component life are very much driven there. So getting in quickly, fixing it, can often be a more effective fix, and the cumulative damage is decreased, increasing component life. A few examples and just a few pictures. It doesn't look that severe. You get a bit closer, it's not very pretty. Dipped IBJ, broken rail 6 months after we visited the site. Fairly obvious, but it's not something necessarily we did anything to prevent in the meantime. A few others, we've seen some pictures of wet spots. Again, doesn't look too bad. People look at it as a geometry issue or a formation issue. Does a lot of damage to the rail. The rail in that situation effectively is super soft track. The deflection is very high, stresses in the rail foot are very high. And if we don't have failures fairly soon, it certainly shortens the life. It's not always the UK, some example pictures from outside of the UK as well. We know what we want to do, lots of bags of ballast there ready to go in. I think the weeds are starting to grow in some of them, but we've got the right idea. It's just getting in there and back to fixing things early. By the time it's this stage, you can see 10, 15, 20 mil of deflection in those areas. You can imagine the rail stresses in those are very high. A couple of others I've been looking at recently. But looking, and as always, I have a focus on broken rails and rail defects. So I've been picking out where did our rails break. I get lots of good pictures now from the engineers locally, close-ups of the fracture face, pictures of the sleeper, comment back saying ballast condition typical, pad condition okay. You go back and then look at the aerial photography, and it's about having more data. That's the location. It's the right-hand rail broke in this picture. It broke about there. Look back further, it's a structure. It's on the end of the structure. It's a transition between the two. The broken rail pictures we got originally, you didn't see any of this, the wider view. You don't see the whitening of the ballast where the ballast attrition has occurred. There's a lot of energy in the track at that point. It's right on the transition, it all makes a lot of sense, but the initial broken rail forms and that sort of thing, none of that information available. So I've been looking further. It's easy with hindsight, I can tell where they've broken. You go back, there's another location, but the picture in the database shows a typical foot failure. Pad condition isn't great. A fairly clean broken or vertical break through the rail at that situation. This is one from very recently. Broken rail, again, foot failure, clean break. A lot of people look at them, they're not that risky. You can already see the misalignment between the rail ends that's occurred there. That's not something you want to run any traffic, or certainly not for any length of time over. Although it's nominally supported, it's on a sleeper. You can see there how the sleeper's dropped and there's a difference in movement there. But a lot of that's the dynamic movement of the track underneath it. Again, the whitening of the ballast. Picture on the left there, where we've got a temporary clamp on it to run it at low speed. But again, look in the background, there's your structure, right on the transition. And this, I've got to find something to do on Saturday evenings, kept going through recent broken rails, which made me think, what can we do more about it? It's not an obvious fault on a track geometry trace, but clearly something's happening there. There's more energy, the ballast is deteriorating, we've probably got a fair bit of voiding. We can start to model. You can take real track geometry data, you can stick in through a vehicle dynamics package, you can put a lot of work in, you can find bits with higher track forces. It may help, but it's quite time consuming to run it, and it's quite hard to locate it all. So tie that back to the specific picture. These are relatively short patches in the track, they're not necessarily long bits, they're not a massive change in geometry. So whether we can pick those up, it's possible, but that's for one type of vehicle. You get an output. So we're doing some work at the moment. I hope to have some load measuring wheel sets on one of our geometry or plain line pattern recognition vehicles to actually measure actual force real time, and then compare that with track quality to see. Primarily I'm interested there with the geometry, which perhaps some of it is around passenger comfort, actually picks up some of the higher forces that we may be seeing and certainly causes some of the deterioration and failures. If you look at some of them, this is the East Coast one. I've shown the slide a few times in the past. Typical broken rail. It's a flashback weld at that point. We've got some voiding and attrition of the ballast again. Certainly not the best pad, but present, you can see the edges of it. Underside of the rail, it's not too bad. There's a bit of pitting on it. That's the pad from the same location. The high strain in the middle of the pad because of the high dynamic loading. Quite a rapid failure of the pad that's broken down completely. The bit you can see around the edge doesn't look too bad, but pretty ineffective, certainly in the middle where the highest loads are. And that's the fracture face on the piece of rail. Now, a lot of what I've spent my time doing is challenging the NDT side of things. Can we find these things? Can we inspect for them? That's what we're trying to look for. It's as far away from the top of the rail where we put the sound in as possible, so from an NDT point of view, a big challenge. You look at some of the facts, well, I'll try to put some things together really as a conclusion. I think low formation stiffness, we get increased ballast settlement, higher ballast strains. We get variations in ballast settlement, and that increases the roughness of the track. Perhaps more frequent maintenance, higher loads, conditions, shorter ballast lives. Stiffer track formation results in lower deflection, lower bending stresses in the rail, so some good things. But overly stiff, we've seen increases in the surface damage, so RCF type damage and similar. can cause problems where the track is overly stiff. Variations in track stiffness greatly increase the bending stresses, as I've shown. We've got results now where we see broken rails directly linked to that. Stiffer track, normally better for higher speed, but the formation is probably the most important bit and the primary determinant of the overall stiffness of the track. The speed we talk about and the stiffness, so the speed of deflection of the wave in front of the train produced in the track, that will increase with that speed will actually increase with stiffness. What's termed critical velocity, where you actually have a high-speed train, relatively soft track. The deflection wave ahead of the train will coincide effectively or approach the direct direction deflection under the train. We end up then with a much more rapid deterioration in ballast and problem locations, probably termed or better known under sort of critical velocity conditions, but equally could be insufficient stiffness. If you look at what we've done, a lot of work to try and reduce broken rails. We've come down from just under 1,000 to under 100 last year. But if you look at some of the distribution, this was back 5 years ago, this is last year. You can see the big increase now in foot failures as a percentage. And whilst it looks quite dramatic, percentage-wise there's some big increases. The numbers are about the same. So overall numbers are about the same, but because we've got better at getting rid of other stuff, managing other stuff, we can reduce those. But foot failures, certainly no sort of decrease. The numbers are about the same, but the percentages are increased. I won't touch on this much. The railway spent a huge amount of time and effort treating problems, but probably not curing them, not permanently. So anything, stone blowers, tampers, all sorts of hand techniques. Peter's touched on some of them. We could do a bit more, perhaps compaction of formation, localised interventions with micropiling and similar. Some of the other equipment that's used widely in other parts of the industry, certainly construction of road and similar, with much larger rollers, more effective compaction, better use of data as well. Ideally, it'd all be nice and perfect on concrete with perfect stiffness, although Mr. Ransom still wants it about 0.5 mil higher at that point. But in the UK, most of our railway wasn't quite like that. We took it out with the shovel, tipped it with horse and cart. There's your embankment and your cuttings. And we live with that today in many cases. A couple of last things just to finish. A bit about new standards and old track engineers' sayings. 2102, the track construction in draft at the moment, due to be published in December. We've actually included some bits about formation. So a bit about, think about the formation stiffness when you're designing it. Think about the change in support conditions. Think about the interfaces, particularly between ballasted track structures or non-ballasted. And we've included a section now at the moment for a minimum stiffness value for formation. First time it's been in standards. It's fairly low level. We've suggested some values that we'd like to try and achieve. It's going to take some work to prove we're getting that and whether we do deliver that or whether those are actually high enough. They're minimum values, but trying to set something for the first time in standards, in the construction standard. And lastly, staff presenter later this afternoon provides some very valuable advice in that situation. He always told me, aim wide, stop it moving initially, don't let it get out of hand. Water's the deadliest enemy. We see it again and again, the problems that come from that. If we stop it moving, we limit the time it's under those dynamic loads. We usually effect a much more long-lasting repair. We end up with a track that lasts longer, more efficient, cheaper, safer. Thank you.